All right, so this chapter will go over control of microbial growth. Okay, so. Okay, norovirus. This was, I was actually involved in scientific studies over control of norovirus as a volunteer patient. Anyway, or not volunteer, I got paid for it. So, okay, so chapter 7. So sterilization, disinfection, antisepsis, degerming, sanitation, biocide, germicide, bacteriostasis, asepsis. Know these terms. Okay, know the definitions of these terms. You will be tested on the definitions of these terms. Okay. Okay. Sepsis refers to bacterial contamination. Okay. Asepsis is the absence of significant contamination. So asepsis is not sterile. Okay. You can use sterilized instruments and stuff, but it can't be purely, everything sterile. Asepsis is the absence of significant contamination. Okay, sterilization is the removal of all microbial life. Okay, commercial sterilization techniques, they measure it by the ability to kill Clostridium botulinum endospores from canned goods. That is the definition. I mean, those things are really hard to kill. So if you killed those, then most likely you've killed whatever else there. Okay, so they test the methods using this. Okay, disinfection is just destroying harmful microorganisms. It is not sterilization. Okay, antisepsis is destroying harmful organisms from living tissue. Obviously, you can't treat living tissue the same way you treat dead tissue, right? You can, or not even tissue, like objects, right? You can put something through a Bunsen burner. You cannot put your flesh through a Bunsen burner. Okay. Okay, degerming, the mechanical removal of microbes from limited area. So thinking like washing your hands would be an example of degerming. Okay, sanitation. Again, sanitation is not complete removal. Okay, it's lowering the microbial counts on using utensils to safe levels. Okay, biocide or germicide, which is a more common term, is a treatment that kills microbes. Okay, side is death. Stasis is inhibiting growth but not death. So bacterial side is killing the bacteria. Bacterial stasis is inhibiting the growth of but not killing the microbes. And the only way to check really is to see if you remove the agent, if the microbes start growing again. Okay. 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 So this question, the answer to this question is what I explained earlier. There's no way to prove that you've killed everything. The only way you can prove you've killed everything is make sure nothing grows. So you have to try to grow everything in every which way, so you make sure that nothing grows. And that is pretty much impossible. So the definition of sterilization in a commercial industry really is to make sure, like even Clostridium endospores are notoriously hard to kill. Okay, so even the endospores will survive. Very little does. Yeah, there's some interesting thing I'll tell you about this problem in a couple of chapters. Okay. Okay. Next thing you guys have to know is the term, the pattern of microbial death. Okay? Okay. So when we treat, okay, the rate of microbial death is logarithmic. Okay? So what this looks like is, well, 90% of them die in the first minute. 90% of the ones that survive die in the next minute. 90% of the ones that survive die in the next minute, etc., etc., etc. Okay, so the rate of death, the blue line will be the arithmetic variable, but it's not really the easiest thing to see because like 3, 4, 5, and 6 look about the same when you look at a line like that. But what you do, the red line tells you the better story, right? The more understandable story. The red line is logarithmic. So every space, okay, it goes down 90%. So it was, to put another way, it goes only 10% survive every minute. Okay. Okay. So what I want you to be able to understand is, like, you'll be tested on this, like, how many will survive after 3 minutes, or if you start off with, you know, 1 million bacteria, how many will be alive after 1 minute, after 2 minutes, after 3 minutes, etc., etc. Okay. Okay. The other thing you have to understand, because the microbial death curve is logarithmic, the larger the population you start with, the longer it takes to kill everything. Okay. So imagine here, if I started here, and if I just started with 1,000 microbes, in 1 minute you will have 100, in 2 minutes you have 10, in 3 minutes you have 1, in 4 minutes you have 0. But right, so at 4 minutes everything is supposedly sterile. But if you have 1 million, well, in 1 minute you have 10,000, or in 1 minute you have 100,000, in 2 minutes you have 10,000, in 3 minutes you have 1,000, 4 minutes you still have 100 microbes, right? And if you stop there, those 100 microbes would grow back very easily. Okay. Okay, action to my membrane permeability, damage to proteins, damage to nucleic acids. Okay. So the answer to this question is yes, and you have to be very careful if you were trying to attack the plasma membrane, because our cells have a plasma membrane as well. Okay. All right, the physical methods of microbial growth. Okay. So heat denatures enzymes. Okay. So all I have to do is cook it. Okay. The thermal death point is the lowest temperature at which all cells in the liquid culture are killed in 10 minutes. Okay. The thermal death time is the minimal time for all the bacteria in liquid culture to be killed at a particular time. Okay. The most important value, and the ones you definitely have to understand, is the decimal reduction time. Okay. The minutes that it takes to kill 90% of a specific population of bacteria at a given temperature. Okay. So if that is 10 minutes, then at 10 minutes, I'll have to kill 90% of the bacteria. Okay. At 20 minutes, I would have killed 90% of the bacteria plus another 90% of the remaining bacteria. So I would have killed 99% of the bacteria. Okay. So I move the decimal over. Okay. In 30 minutes, I would have killed 90 99.9% of bacteria. In 40 minutes, I will put 99.99% of bacteria. Does that make sense? That's where we get like all these terms that kills 99% of bacteria and stuff. That's where these terms come from. Okay, so make sure you understand how DRT works. Okay. Okay. So moist heat sterilization. Again, moist heat is actually even better than dry heat because it attaches to the water molecules attached to the bacteria more, and therefore it denatures the proteins faster, etc., etc. Okay. All right. If you combine both of them, you can combine steam under pressure. I can raise my steam to higher temperature, and the higher pressure will also drive the steam into the bacteria, which will kill them faster. And one of the ways to do that is something called the autoclave. Okay, like hospitals and stuff will all have autoclaves. So whatever instruments you need to use, if it's not one-use disposable, then it's autoclavable, and you shove them into an autoclave. Autoclave basically steams the crap out of it at very high temperature and very high pressure. Okay, so water usually boils at 100 degrees. Okay, so putting it in an autoclave increases the boiling temperature of the water because it puts it under higher pressure, so you get more hotter water. Okay. Okay. And we put test strips on it. There are little pieces of tape that turn black once you've reached sterility. Okay. So this is the tape. Okay. So they turn black. Usually it's not this nice. Okay, pasteurization does not kill everything. When you pasteurize something, the reason why you pasteurize it is if boiling it affects the taste. Like if you boil, you boil wine, all the alcohol will be gone and the wine will be useless. If you boil milk, the milk doesn't taste very good. Okay, so one of the ways to get around that is to not kill everything, but kill most bacteria. And that's what pasteurization actually is. Okay. All right. So dry heat sterilization. So kills by oxidation. You flame it, you incinerate it. Hot air sterilization. Okay. Okay. There are things that you don't want to cook or heat, and therefore you filter it. Okay, use for heat sensitive material, and you filter, you run it through a mesh that traps all the bacteria or and keeps everything else out, and that after you pour it out, it becomes clean. And this is what you can do for. I'm not sure how interested you guys are doing like missionary work and stuff like that, but there are those water bottles that have filters attached to them, and you can put them in rivers, and it'll filter out all the bacteria in there, and you can just drink the water afterwards. That's what this stuff is. Okay. Okay. Low temperature has a bacterial static effect, which means it does not kill the microbe. Okay, they come back. So in the refrigerator, food goes bad. It just goes bad slower than if it was outside. Okay, deep freezing, like dropping in liquid nitrogen and stuff, that deep freezes them, but they come back. Okay, lyophilization, freeze drying, like the astronaut ice cream and stuff like that, the freeze dry ice cream. Okay, that kills the bacteria. That stops the bacteria from growing when they come back. In fact, they just established last week bacteria can stay in space where everything is basically freeze dried after like 3 years. Okay. Okay. Desiccation, using salt as a way to desiccate. Okay. It causes the plasmolysis of bacteria. Okay. So the bacteria dries out. Okay. Ionizing radiation. Okay. Ionizing radiation is strong enough to break DNA. Okay. It ionizes water to create hydroxyl radicals. Those radicals start damaging DNA and cause lethal mutations. Okay. Ionizing mutations are X-rays, gamma rays, electron beams. These really, really high energy waves that can cause DNA damage. X-rays can barely cause DNA damage. So you can get X-rays and stuff, and it's not going to do anything to you. But if you do that over and over and over again, it will accumulate. Okay. Okay. Non-ionizing radiation, ultraviolet, one of the beams of ultraviolet usually doesn't is usually strong enough to cause ionizing radiation, but at 216 nanometers it doesn't. But it does damage DNA because at that frequency it creates something called a thymine dimer. Okay, whenever you have two T's together in DNA, which is pretty often, I think it's somewhere along the line of 10% or something like that. They bind together, and this causes in humans, this really doesn't do very much because we can repair it. In bacteria, they're worse at repairing this type of damage. Okay, which is why non-ionizing radiation is actually useful for destroying bacteria. Okay, what was I about to say? Okay, so a couple of things about non-ionizing radiation. It's not something you have to worry about unless it's exactly at 260 nanometers and stuff. Okay, cell towers, the 5G cell towers and stuff like that, and the idiots that are freaking out about 5G cell towers causing radiation. The first thing you ask is the radiation ionizing or not ionizing, and they will immediately lose any logic because they have no idea. If it's not ionizing, it's not going to cause DNA damage. Okay, so you don't have to worry about it. 5G will not give you cancer or cause coronavirus infections. Can't believe I had to like sit down with my students and debunk that, but I had to. Okay. Microwaves. Okay. Actually do something different. Microwaves kill by heat. They vibrate water bombs, and vibrating water bombs generate a tremendous amount of heat, which is why microwaves heat things up very quickly, especially if they're wet. Okay, but they're not especially microbial. Okay. Okay. Oh, by the way, not this using UV light is a great way to help sterilize your house from coronaviruses and stuff. But do not look into the light. Okay, use it appropriately. Okay, So the radical forms of oxygen is what does the killing. Okay. The others you should be able to figure out on your own. Okay. All right. So principles of effective disinfection: the concentration of the disinfectant, if there's other organic matter in the way, if there's what the pH is, and how much time you put in it. Okay. Okay. We'll skip use the dilution tests. This diffusion method is basically the one of the most common ways. So what we look for is we take no disc of paper and we soak it in whatever we want to test to see if it's antimicrobial or not. And we dip it in different concentrations, okay? And then we put those little discs on a plate of bacteria. And you can see in the next slide what happens, okay? So here, okay, you can tell, so the liquid will spread out from the disc a little bit, and as it spreads out, it'll become lower and lower and lower concentration. Okay, so here we can see the zone of diffusion. Okay, and you can see that chlorine is much more effective. Blow this up. Okay, chlorine is much more effective than, oops. Okay, the other ones except hexachlorophene. But you can see there are some that are completely ineffective. Like the only thing that affects Pseudomonas is chlorine. The other ones are gram-positive antimicrobial, or they attack gram-positive bacteria, but they leave gram-negative ones alone. Okay, so you know. Okay. So if you wanted to disinfect a surface contaminated by vomit and a surface contaminated by a sneeze, why would your choice of disinfectant make a difference? One, there are different pHs, right? So the vomit is going to be a lot more acidic. Okay. Two, the vomit will have a lot more stuff and have a lot more like enzymes and stuff and stuff in your nose, and therefore you need to use basically a stronger antibiotic. Okay. Okay. So we usually use this diffusion test. So make sure you understand this diffusion test. Okay. Phenol and phenolates. These injure lipids and plasma membranes, causing leakage. You shouldn't. I mean, if you get on you, they can also cause cell damage to you too. Okay. Oh, sorry about that. All right, chlorohexidine. It's used in surgical hand scrubs. It's also used to clean cages and stuff. Okay. Okay. Ship essential oils. All right. Iodine. Okay. Iodine, the tincture is an iodine solution in aqueous alcohol. Um, Iodine inhibits protein synthesis and alters membrane. Um, this was much more common when I was a kid. Like if you got a cut and stuff, they swabbed you with iodine, and that hurt a lot. But it kill all the bacteria. So chlorine is an oxidizing agent. Okay. Alcohol denatures proteins and dissolves lipids. Okay, this is what the hand sanitizer is. Your hand sanitizer is 70% alcohol. It should be at least 70% alcohol to actually work. Okay. Okay. It denatures lipids and dissolves lipids. This is why the hand sanitizer is really useful against coronavirus, because the outer layer of coronavirus is actually lipid. So the hand sanitizer does work. Okay. Okay, we'll skip the heavy metals. Okay, but you can see metals and stuff do work as a disinfectant. That's why like copper surfaces, you probably heard a little bit about that. They actually prevent growth. Okay. So you can see the effectiveness of various antiseptics. Okay. Soap and water, blah, blah. So soap and water, if you see it, it doesn't seem to be very effective, but that's just nipping it in. Like most of the soap and water, you're washing off the bacteria more than you are trying to kill it in there. Okay, the washing off separates the scrubbing separates the bacteria from your hand and it runs off in the water. Okay, so we'll get this. Okay, aldehydes have this ability to cross-link proteins. Okay, what it basically do is it takes one end to grab onto one protein, and the other end of it will grab onto another protein. Now these things are cross-linked to each other, and neither of them can move away from one another. And if you randomly cross-link stuff, you'll get a big blob of protein that can't do anything. If you do that enough, the bacteria dies. Okay, so I'm sure you've heard of formaldehyde. Okay, formaldehyde is what they inject into dead people, right? So it preserves the body by cross-linking a bunch of proteins. Now the bacteria are dead inside, and even if there's live bacteria growing out of you, they don't know how to uncross-link the protein, so they can't like eat it. They can't break it down. Okay. All right, we'll skip that. Okay, we'll skip that. Skip that. Okay. Peroxides, okay, are oxidizing agents, okay, pyrogens, etc., etc. All right, so that ends this chapter. Like I said, this chapter is short. Next chapter is pretty short, but it's pretty long, but I'm going to shorten it a little bit. Okay. All right, I'll see you for chapter 8.